My name is Tomasz Tkocz. I'm from Princeton University, and I'm going to talk about upper and lower bounds for suprema of canonical processes. And this is based on joint work with Rafał Latawa, which I did a couple of years ago as a PhD student under his supervision at the University of Warsaw. So let me start off by introducing the setup we are going to deal with today. So suppose we are given a sequence of independent random variables, x1, x2, etc. And we assume that they are normalized in a way that they have mean 0 and variance 1. And we've got a finite subset of Rn. And then, given these two things, we define a canonical process, xt. We say it's based on that sequence xi, and we define it as x sub t is just a dot product with that vector x, which has iid coordinates, and that index vector t, which is a vector in Rn. So it's just the sum from 1 to n ti xi. And given such a canonical process, the main question we would like to address is how big is the supremum? This is the main theme of this workshop. We want to estimate the supremum of a canonical process, the expectation. and just as a technical side remark, if the variables xi or the set t are symmetric, estimating the supremum of xt amounts to actually estimating the supremum of the increments xs minus xt over all s and t from t. And this is simply because I can write twice the supremum of xt as supremum of xt plus supremum of minus xs, and then just put it together. Okay. So again, our main question is how big the supremum is. And as we've seen in Jelani's talk, for the Gaussian case, namely when xi are standard Gaussian random variables gi, then the supremum is controlled by the gamma 2 function of t. So we have an upper and a lower bound, and they are up to multiplicative constants. So the meaning is that really the value of the supremum is captured by that geometric quantity gamma 2, and it depends only on the metric space t d2, where for d2 we use just the Euclidean distance. d2s comma t is the Euclidean distance in Rn between s and t, and later we will see that actually this is related to the fact that we have the Euclidean distance comes from the fact that we look at the second moment of the increments, gs minus g2, gs minus gt. And the goal for today is we would like to obtain similar bounds for other canonical processes. So we know how it works for Gaussians, but what about other xi? So it's been understood in several important cases besides the Gaussian case. So for instance, very recently for the Bernoulli case, when xi take the value plus minus 1 with probability a half, recently the so-called Bernoulli conjecture has been settled by Witold Bednož and Rafał Latawa, which amounts to really understanding the supremum of a canonical process based on Bernoulli random variables. But we also have some earlier results. So, for example, in the case of the exponential family, so if xi have densities which are proportional to e to the minus absolute value of x to the p, and p ranges between 1 and infinity, then there are also matching upper and lower bounds for the supremum based on canonical, based on independent exponential random variables. More generally, this was generalized by Rafał Latawa, to the case when xi have log concave tails. So namely this function log probability that absolute value of xi is bigger than t. This minus of this function is convex. This is straightforward. This is a generalization of Talagron's result. And today we are going to talk about yet another generalization of this log concave tail case. Namely, we will look at random variables which have moments growing regularly. We will define later what it means. Now, for now on, just to establish the notation, we'll look at the pth moment of random variable xi, which is the usual thing. So to give some sort of overview and recall the ideas from the Gaussian case we saw in the morning, let me go over again two upper bounds. The first one will be very easy. The second one, we will employ the chaining argument. But now I'm going to talk about canonical processes based on general random variables. So I'm not going to assume almost anything about xi. In the morning, Jelani did all the same job really for the Gaussians, but now let's have a look how it can work in more general setup. So let's start with an easy upper bound. So I'm looking at the supremum expected value of the supremum of the increments, and well, this is just Jensen's inequality. Instead of looking at the expected value of the first moment, I can look at the expected value of the pth moment. This is an upper bound. And then we just use a union bound, meaning that supremum of non-negative things can be estimated simply by their sum. So this is what we do here. And now our index set is all the pairs from t, so it's of the size t squared. So we pull this out, t to the 2 over p outside, and we end up here with the supremum over all pth moments of the increments of our process. And now if the size of the t does not exceed e to the p, which means that we are in the regime when the size of t is exponential with respect to p, then we get an upper bound of the following form. The expected value of the supremum of the increments can be bounded by an absolute constant times the diameter measured using the pth metric. It's actually a pseudometric, and it comes from our random variables, and we just measure the diameter of our index set t. So again, this is an easy upper bound. Once again, we have finite set which is at most exponentially large. P is a free parameter in this estimate, and then we estimate the supremum by the diameter. But on the other hand, if we are interested in the lower bound, we can think of the following sort of reverse inequality to this easy upper bound, and we will call this Sudakov minoration principle. So let me define this. So if I have a canonical process xt, I'm going to say that it satisfies the Sudakov minoration principle, SMP for short, with a constant kappa if for every number p at least 1 and for every subset s in T, such that the subset is exponentially large. So previously for the upper bound we cared about sets which are at most exponentially large. Now we care about sets which are at least exponentially large with respect to p. And we want the set to be such that the points are separated. So the pth distance between every S1 and S2 is at least u. So if the set is not too small and its points are u apart, then we say that this process satisfies the Sudakov minoration principle if we have a corresponding lower bound for the expected value of the supremum by that gap between the points in S. So just to recall it here, once again, we say that SMP holds if for sets whose points are U separated, they are U apart, and there are at least e to the p sets, points in the set, then the lower bound is kappa times U. And to relate it to what we've seen for the Gaussian case, namely the classical Sudakov's minoration principle stated by Jelani, was that the expected value of the supremum of a Gaussian process is this one single term in Dudley's sum, which can be phrased as the supremum over all epsilon times square root log n of t d2 epsilon, which is the size of the smallest epsilon net of the metric space associated with that Gaussian process. And now just to see that these two things are really the same, that we are generalizing this concept, let's see why this classical Sudakov's theorem matches what we introduce here. So suppose I have a classical Sudakov's theorem, and I want to show that SMP in that general notion that we introduced just now holds as well. So I choose a subset S in T, which is exponentially large. So we fix P, we fix S, whose size is at least e to the P. And then we assume that the points in S are U separated. And then, so we write this down. Distance between S1 and S2 is at least U. This is what we assume. And now the crux is that the pth metric associated to the Gaussian process being the pth moment of the increment GS1 minus GS2 is proportional to the second moment. We know how the Gaussian moments behave, and the ratio is roughly square root p. So we can understand the pth moment fairly easy in terms of the second moment. And because p is at most log s, we have that the Euclidean distance between S1 and S2 is at least U over the square root log s. So every 2 points in our assumption, it really is that every 2 points in S are U over square root log s apart, measured in the usual Euclidean distance. So if I choose epsilon to be, say, half of that quantity, how far the points are, then to cover S, I really have to use as many points in my epsilon net, because epsilon is smaller than, the distance between every 2 points. So this is n. N is equal to size of S. So the classical Sudakov gives us this epsilon, which is a half times U over square root log S. This square root log n becomes square root log S. So these two things will cancel, and we end up with an absolute constant times U, exactly what we wanted to show. So this is how this thing works for the Gaussian process. And now, so we started off with an easy upper bound. We just did a union bound. And now let's try to soup it up. Let's try to improve that bound by employing a chaining argument. So we will go over Fernic's argument that Jelani showed, but for an arbitrary canonical process. And we will see how this notion of the pth metrics kick in this argument. So let's go over the objects we need to run the chaining argument. So we fix an increasing sequence of partitions of T. So if I imagine T as this rectangle, then I partition T. I have actually a family of partitions. And I require that the first partition is trivial. It's just T itself. And I require that the size of nth partition is at most 2 to the 2 to the n. So it's double exponential. And having chosen a partition, we form sets Tn, which are some representatives from every partition. So for every an, we form Tn just by selecting from each piece of the partition 1 point. So Tn is the set of the red dots here in this picture, and particularly the set of representatives is of the same cardinality as the size of the partition, which is at most double exponential. So we have representatives, and now when we pick any point in T, we call the representative, which is from the same piece where T is, pi sub n of T. So this is the unique point from the same set from an as T is. Okay, so this allows us to now build the chain. So by the telescoping trick, xt minus x pi 1 can be written as the sum, which really is finite, because set T is finite, everything here is finite for simplicity. So we can break an arbitrary increment xt minus x pi 1 of T into links of our chain. So smaller pieces. So once again, this is our chain. And recall that we use pith metric associated to our process just by taking the pith moment of the increment xs minus xt. And now we are interested in bounding the supremum of xt minus xs. How are we going to do this? Well, let's first have a look at sets of omega. For fixed n, t, and u, let's have a look at set of omegas for which the increment x pi n plus 1 of t minus x pi n of t. So the nth piece, so the nth link of our chain is controlled, its size is controlled above by some fixed number u. We fix some parameter u. And we require that the nth link of our chain is at most the distance between pi n plus 1 of t and pi n of t, those approximations of t at the nth level coming from the partition, from the set of the representatives. And we measure the distance. So this is the main difference with respect to what we've seen in Jelani's talk. So here we don't use the usual Euclidean distance, but we stick to the 2 to the nth distance between those two approximations of point T. So here is the crucial thing in this argument, because now we don't, for an arbitrary process, the point being that we don't know how the moments grow, so we allow some flexibility. We don't stick to the second moment, but we choose higher and higher moments to hopefully control things better and better. So this is a set of good omegas for fixed n, t, and u, but we are interested in bounding above the increment, which is broken by this chain into smaller pieces. So we also are going to look at the set of omega u being the intersection of those good sets over all possible n and all possible t. Okay. So by usual Chebyshev's inequality, we can bound the probability of the complement of our good set just by. So remember that this d2n, 2 to the n, is just the 2 to the nth moment of the increment. So of this thing here. So by Chebyshev's, we get u to the minus 2 to the n for that probability. So now by just using the union bound, we can get the probability of the complement of omega u bounded by, so this intersection will give us the sum over n. Now this intersection over t, so when t varies, those points, those approximations, pi n plus 1 of t and pi n of t, those points live in t n plus 1 and t n. So in this union bound, we don't have to use the whole t, but we just use, because those approximations are t n plus 1 and t n. So we've got those bits here coming from this intersection over t. And the probability of omega n tu complement is estimated here. So we get this piece u to the minus 2 to the n. And recall that we set up partitions which do not have too many elements. So the set of the representatives are at most of double exponential size. So when you put all those bounds here together, you get a double exponential decaying sum, which is a subsum of the usual geometric series. So it can be bounded really so that sum is of the order of the first term. So we have to be careful that u is large enough. So we assume that u is at least 16, and then we get an upper bound for the complement, for the probability of the complement of omega u. So that probability is hopefully tiny. And what happens on omega u, so this is the set where we are interested in. Well, on omega u, we have good bounds for each and every link of our chain. So the supremum over all t's of that increment xt minus x pi 1 of t can be bounded just by the usual triangle inequality by the supremum. So we keep the supremum here. We have the sum over all increments coming from finer and finer approximations. And now each of these links we are on omega u. Well, it's controlled by the u times the 2 to the nth distance between those approximations. So we get this quantity, supremum over t, sum over n, d 2 to the n of pi n plus 1 and pi n. And we call that supremum s. We have this factor u, scaling factor u outside. That's good. So once again, on omega u, we get the bound for the supremum of the form u times some quantity s. Okay? And this just allows us to estimate the tail of, rescaled supremum of xt minus x pi 1 of t. Well, on this set, we are on omega u complement, and we have a good upper bound for that. We've seen that before. Having obtained a tail bound allows us to bound the expectation. We just integrate by parts this tail bound, and we get an estimate for the expectation which is proportional to s. So we get an absolute constant times s. Okay? And now we are interested in bounding the supremum of all the increments. So far, we've obtained a bound for supremum of increment being xt minus the first approximation of t. Well, but if I have an arbitrary increment just by using triangle inequality and the fact that supremum of the sum is at most the sum of the suprema, I break this into those pieces that I've understood already. So I have supremum of xs minus the first approximation of s. Then I have to have this middle term which controls the increments of the first approximations of x and t. And then I have the last term which is of the same form as the first term. So if I take the expectation, I will have 2 times what I found for the bound of the supremum of the increment of t and its first approximation. So So this is this quantity. And we have this middle quantity, it's supremum here. Well, and we treat this one crudely. We just use the union bound again. So we bound the supremum. So again, we swapped supremum for the sum because we've got non-negative quantities. And we don't use any Jensen's inequality now. We just stick to the first moment. It's written here. So we have the sum over all S and T expectation of this quantity. And, well, this is the distance, the first distance measured D1, measured according to D1 between x pi 1 of S and x pi 1 of T. Well, and we don't care. We just estimate it by the diameter of T measured in D1. And we have the size of T, which is at most a constant. So all in all, what we get is an absolute constant times S plus the diameter of T measured using the first moment metric. OK, and let's recall what S was. So S was the supremum of T, sum over N. And then we have those growing distances of between finer and finer approximations. And now let's observe that pi n of t and pi n plus 1 of t, they live in the same piece of a partition, because pi n plus 1 of t comes from, finer approximation than pi n of t. So in particular, it lives in the same piece of the partition as pi n of t. And we call that piece a n of t. So that's the unique set which contains t from which that representative pi n of t is chosen. But that piece of partition also contains pi n plus 1 of t. So this thing can be estimated. So I have two points from the set a n of t. So I just estimate the diameter, the distance between them by the diameter of that set, and that diameter is taken with respect to the 2 to the nth metric. That's the thing. And this sum starts from 1, okay? When we look at the 0 term of this sum, if we let n to be 0 in this sum, we would have the diameter measured using the first distance of a0 of t. a0 of t is the only piece of the first partition, which is the set t itself. So we have this guy here, this diameter of t. So we just incorporate this in S. This does not depend on t, so I can put it inside the supremum. And this leads to the following definition of the gamma x functional. So remember that we just fixed an increasing sequence of partitions. And everything was done with that fixed sequence of partitions. And I can, for gamma x of t, I can optimize over those partitions. So that's why we write infimum over all admissible sequences of increasing partitions. Admissible meaning that they are not too big. The size of the nth partition is at most double exponential. And then we've got this S quantity here with the 0 term, which came from that leftover we had. And the difference between the gamma 2 functional now and this general gamma x functional is that we use 2 to the nth. We use different metrics at different levels. And hence, we established the following fact, which was noted independently by Rafał Latawa and Shahar Mendelssohn. For any canonical process, we always have an upper bound of the supremum of the increments in terms of the gamma x functional. So for the upper bound, so the moral here is that for the upper bound, we don't have to use anything. It's always true that the supremum is bounded, is controlled by the gamma x functional, which is cooked up to the process using the growing metrics. So once again, so we've got in full generality the chaining upper bound, which holds for any canonical processes. So this is the definition of gamma x. And now, just again as a small remark, let's have a look what happens when we have a Gaussian process. So when the sequence of independent random variables are Gaussians, actually they don't have to be independent. The point being that the 2 to the nth diameter now is proportional to the Euclidean diameter, which is used in the definition of gamma 2. But we have to rescale by the factor of square root 2 to the n. And this comes from, again, the fact that the Gaussian moments grow like square root of p. So that's why gamma g is really the gamma 2 we have already seen. Okay, so to sum up what happened so far, we've established two upper bounds. The first one very easy, the union bound, and the second one it's chaining refinement. So we bunch up together similar random variables, we form chains, and then we get this gamma x functional, which hopefully captures how big the supremum is. So having said that, we can pose now two goals. So the first one, the ultimate goal, let's say, would be to reverse the gamma x upper bound and obtain gamma x lower bound, so that really the supremum is of the size of that geometric quantity gamma x of t. But the easier goal would be to actually establish first the Sudakov-minoration principle, which is in the spirit reversing the easy upper bound. So once again, what that was, well, we would like to show that for every subset t, which is at least exponentially large, whose points are u apart, the supremum of the increments is at least proportional to that u, how far the points are apart in the set. So once again, we have ultimate goal, the easier goal. So the ultimate goal is the gamma x lower bound. The easier goal would be the Sudakov-minoration principle. And now the easier goal should actually be a consequence of the ultimate goal. So again, let's have a look why, if I establish the gamma x lower bound, actually it implies also the Sudakov-minoration principle. Let's have a look at a simple argument why, reversing really the stronger upper bound would imply reversing the easier upper bound. So I assume that I have established gamma x lower bound, and now I want to show the Sudakov-minoration principle. And here I will assume that xi are independent. So we fix p, we fix the subset S, which is at least e to the p. And now we choose n such that p is between 2 to the n and 2 to the n plus 1. And the trick here is to consider the product set S times S. We call this S tilde. And for an S whose coordinates in this S and in that S are S1 and S2, we have that, the canonical process XS, the way it's defined, it boils down to saying that XS is just the sum of XS1 plus XS2, because again, XS was just the dot product between X and S. So really estimating the supremum of the increments on the S set should correspond to estimating the supremum on the product set. So let's have a look why this could be true. So if I write 2 supremum, 2 the expected value of the supremum on the S set, well, this is and this can be written, as 2a is written as a plus a. I just use different letters which index the supremum. And now the supremum of the sum is at least the sum, the the sum of the suprema is at least the supremum of the sum. So I can put all together xs1, xs1 dash, xs2, xs2 dash, and I get the increment xs minus xs dash. And now s and s dash being points in the product set. And I'm assuming that I know the gamma x lower bound, so I can lower bound this supremum by gamma x of s tilde. And now s tilde has the size of s squared, which is at least e to the 2 to the p, e to the 2p, which is bigger than 2 to the 2 to the n plus 1, which is at least the size of the n plus 1 partition. If we fix the optimal partition for that gamma x of s tilde and use it here, we have that the size of s tilde is at least the size of an plus 1. So therefore, there must be a set in that partition which contains 2 points from s tilde, because its size is bigger than the partition. So let's call these 2 points A and B, and they have components A1 and A2, B1, B2 from S. And then, well, the gamma x functional of S tilde is at least, you know, the gamma x is defined as that sum over n. So I just take the nth term in that sum, which is the 2 to the n plus, I take the n plus 1 term in that sum, which is the diameter 2 to the n plus 1 of A. And then, well, this diameter is at least, because A contains 2 points, A and B, so that diameter is at least the distance between these 2 points, which is this pth moment. And now using independence and the fact that the random variables have mean 0, simply by using Jensen's inequality, I can average out you know, the second fiber. Those A2 and B2 can be averaged out, and I'll get just the increment between XA1 and XB1, the pth moment. And this we assume is at least U, because we assume that, you know, the points in S are U separated. So reading this all together gives us that the supremum on S is bounded below by a constant times gamma x, which is at least U. So we get the Sudakov minoration principle in this case. So this is showing why, you know, things are how they are supposed to be. So what is known about the ultimate goal and the easy goal? Well, so let's have a look at the following grid. So here we have Sudakov minoration principle. Here we have gamma x lower bound. For the Gaussians, we know 2 things. Sudakov's classical theorem was established by Sudakov in 1969. The gamma x lower bound was established by Talleyrand in 1989, which is known as his famous majorizing measure theorem. Now, in the Bernoulli case, so xi are independent plus minus 1 symmetric random variables. It's known that the Sudakov minoration principle still holds. That was established by Talleyrand. Well, gamma x, as it was written, does not lower bound the supremum of Bernoulli process. But anyway, you know, the lower bound for the supremum of the Bernoulli process, as we said a few slides earlier at the beginning, was well understood by Bednosh and Latawa. But gamma x is not cooked up well for that Bernoulli case. However, for the exponential family, we have Sudakov minoration principle, as well as the gamma x lower bound, and that was generalized also by Latawa to the case of log concave tails. So when xi have log concave tails ti, then the Sudakov minoration principle holds. To get the gamma x lower bound for such random variables, we also have to assume something about the decay of that tails. They may not decay too rapidly, too quickly. So the tail at T2 is assumed to be related to the tail at point T. And this is also, well, this assumption is sort of manifested in the Bernoulli case, because the tails of Bernoulli are, you know, it's 1 and then 0. So they decay rapidly. So they do not satisfy this assumption. So the fact that we've got an X here is manifested in this assumption as well. And let me also mention that the Sudakov minoration principle has been thoroughly studied in the dependent setting as well. Here I only care about canonical processes based on IID random variables, but you know, Sudakov minoration principle makes sense for any random vector and its canonical process, and that was studied in 2 papers by Latała and then also by Witold Bednoś, and they consider log concave random vectors, and they consider random vectors which satisfy concentration assumptions. So you know, as usually we want to deal with dependence, and they dealt with dependence in those cases. But now let me go back to establishing the gamma x lower bound as well as the Sudakov minoration principle in the case when in the case when we don't have log concave tails, but we know something about moments. So we want to generalize this last piece of this table. So if a random variable y has a log concave tail, t of t, which is probability that y is bigger than t, then it's a nice exercise to show that the moments of y can be compared. So if I fix p bigger than q bigger than 1, the larger moment can be compared by the lower moment, and we have to pay the ratio p divided by q times some constant alpha. Moreover, if the tail does not decay too fast, so that's the assumption, then we can also reverse that tail behavior in a sense. Then the tails have to grow in a sense. So then there is a beta which is larger than 1, such that the beta times pth moment is at least twice the pth moment. And again, this assumption will not be the case for Bernoulli random variables. The moments are constant of Bernoulli random variables. So we won't have the phenomenon of doubling pth moment at some higher moment. Okay, so that's why we introduce, so to generalize that log concave case, we introduce 2 definitions. We say that moments of y grow alpha regularly if, you know, higher moments can be compared up to constant alpha by lower moments times the ratio p over q. And we say that the moments of y grow with speed beta if we have what we had in the previous slide. Beta times pth moment is at least twice as the pth moment. And now let's assume that we've got a sequence of independent random variables which are normalized, meaning mean 0, variance 1. And if the moments of the xi grow alpha regularly, then the canonical process xt satisfies the Sudakov minoration principle. That's the first result. The second result is, so this settles the easy goal. We establish the Sudakov minoration principle in the case of moments growing alpha regularly. If the moments grow alpha regularly, and on top of that with speed beta, then we can also obtain the gamma x lower bound. So there's a constant which will depend on alpha and beta, such that the supremum is bounded below by that constant times gamma x. And we, of course, always have that upper bound. So in that case, we really can say what the supremum is equivalent to. It's equivalent to gamma x of t. And now let me just very briefly sketch the idea of the proof of these two theorems. Well, it will be again a reduction argument. So we know so we take for granted Rafał's result for log concave tails, and we want to reduce the case of moments growing regularly to that case. And how is it done? Well, so again, by Latała 97, we know that if the tails are log concave, and if additionally that function. So now I'm going to use minus log of the tail. This will be a more convenient function. So if the tail is log concave, then this function is a convex function. It starts at 0 and it increases. So it looks like here. So this is an I. It's a nice and convex function. And moreover, that assumption of the tails do not decaying too fast amounts to saying that this function does not grow too rapidly. So there's this doubling condition, which guarantees theorem 2 in this case. And what in our case? Well, so alpha regularity of moments implies that this function Ni satisfies this pointwise inequality. So if I rescale t by lambda and by some constant which depends only on alpha, which is in the definition of alpha regularity of moments, then I know that Ni of that rescale t is at least lambda times Ni of t. And this holds for every lambda and t which is not too small. So this is what we get from the alpha regularity assumptions when we try to translate it to the tail function. And now, well, this condition should have something to do with convexity. Well, we will see that functions satisfying this are, in a sense, almost convex. If they are almost convex, then hopefully we'll be able to use Latała's result, which covers the case when I is convex. So there is the following basic lemma. I'm going to state the simplest possible version of the lemma we may need. So we assume this inequality, but let's suppose that C alpha is 1, and this holds for all t, not t large enough. This just causes another technical issue. Let's suppose that this holds for every t, and C alpha is 1. So then we've got a function which is maps R plus to R plus, satisfies this inequality. F lambda times t is at least lambda times f of t, for lambda at least 1 and t at least 0. Well, and this assumption tells us that, if f of 0 is 0, which is also guaranteed by this assumption, I just plug in lambda equals 2, say, and t equals 0, I get that f of 0 must be 0 from this. So for a function which is 0 at 0, this assumption really means that those slopes are increasing, which is exactly the case for a convex function. So the hope is that maybe just by this assumption, we can say that function is close in a sense to a convex function. Well, and that's the case, actually. This function may not be convex itself, but it can be sandwiched between a convex function and its rescaled version. So the claim of the lemma is that for an f satisfying this, there is a convex G such that we have this sandwiching result. Now, so this is the lemma here, the statement repeated. And how do we show this? The assumption really means that fs over s is an increasing function. As we said, those slopes are increasing, and they are equal fs over s. And now if we integrate this ratio which measures the slopes, which we know that are non-decreasing, we get an integral of a non-decreasing function, which is going to be convex. But this function, g of t, defined as the integral, is convex. Moreover, it's bounded, because this ratio is non-decreasing, it's bounded above by t times the largest value of the integrand, which is f of t over t, which is f of t. So we get one bound in that sandwich we want to make. Well, what about the lower bound? This is also very easy. So g of 2t is at least the integral of from t to 2t And now we bound the integrand by its lowest possible value, which on this interval is, again, f of t over t. We multiply by the length of the integrating interval, so we get f of t again. So that's the proof of the lemma. So again, alpha regularity of the moments will essentially assure that this function ni may not be convex, but is sandwiched between a non-decreasing convex function, let's call it mi of t, and some rescaled version of that function. And then, well, we take this function, which we get from the lemma, and we look at e to the minus mi. And we say, let's take yi, which is the log concave random variable with this tail. And because of that sandwiching, we can also find realizations of our random variables, which will satisfy this sandwiching bound. So xi is, bounded above and below by a random variable yi, which now has log concave tail. And because of this point was bound, any estimates for the suprema of yi will carry over for the bounds for suprema of processes based on xi. And this will handle the Sudakov's minoration principle. If we want to deal with the gamma x lower bound, well, we will notice that the assumption of the fact that the moments of xi grow with speed beta will translate to this kind of inequality, which will again force this function mi of t, which is convex, to satisfy something similar. And that was Latawa's assumption. So we can use again his result and reduce to that case. So this is roughly the sketch how we reduce. I'm running out of time, so maybe I won't go over this last proof. This is the last slide, just to comfort you and your hungry stomachs, maybe. So we established the Sudakov minoration principle under the assumption of alpha regularity growth of moments. But we can ask a question, well, what's the optimal assumption actually? So say I get a canonical process based on IID random variables, and I want to establish Sudakov minoration principle. And this fact tells us that in such a situation, it's actually necessary for the moments to grow alpha regularly. Meaning that if we assume that Sudakov minoration principle holds for canonical processes based on IID random variables, then no way the moments have to grow alpha regularly. So in a sense, this is the optimal assumption for the Sudakov minoration principle. Well, and as you can see, the argument is not too long, but maybe I'll give up. The point being that you just have to cook up a clever set and then check the details. And that's it. Thank you.